So the next topic is implementing Java AtomicLong. And this is an important class to be aware of. It's very commonly used, probably the most common of the atomic classes that are in the atomics package. And I'm going to first show how to use it, how to implement it using the Unsafe class, and then we'll take a look at another implementation of a different type using var handles, so you'll get a little flavor for both. So AtomicLong, as the name suggests, contains a long value that can be updated and or read from atomically. Under the hood in Java 8 and before, Java 7, Java 6, Java 5, blah, 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 back to the beginning of time, the AtomicLong implementation methods used the compare and swap long unsafe method. And here's what it looked like back in the day. So keep in mind, this is Java code. So this is code that's written in Java, but it uses some very powerful Java features to work effectively. And the first thing you can see it does is it defines a local field called value, which is a long, and it's defined as volatile. What does that mean? It just means that these are going to be atomically read from and written to whenever operations are applied to this value. Then it also defines another field called value offset. And this takes a little while to get your head around. What this basically is this is the offset in bytes from the beginning of an instance of an AtomicLong. So if you have an AtomicLong, it's an object in memory, and there's going to be some stuff at the beginning, typically a virtual pointer, just like C++, that points to a virtual table, if you're familiar with how virtual method dispatching works in Java or C++. And then it might include some other stuff, but at some point it's going to include the value field, and that'll be basically an 8-byte quantity because it's a long. And what we're doing here, and this is really funky, we're using the static initializer block, which is going to be automatically run whenever the first instance of AtomicLong is created. By the time the first instance of AtomicLong is created, this static initializer block will have been run. The time at which it run is probably defined very specifically in the Java memory model, but the thing to think about is before anything happens with an object of AtomicLong, this piece of code will have been run. And what it does is it uses Java reflection to go find the value field. So we're looking this field up by its name using reflection, and we're finding out what the field offset is from the beginning of an AtomicLong object. And that value is being stashed into this field called value offset. So this tells us how many bytes from the beginning of the object the value field will reside in. Now you're probably asking the question, why on earth do we care about this? And I'm going to show you why in a second. So to understand why we care about this, let's take a look at a method that might be provided by the Unsafe class. This would be a class, this is written in Java, but it's going to use some low-level stuff that's coming out of the Java virtual machine layer, which will be native methods. So here, get and add long. Unsafe get and add long atomically updates a value at an offset in the object. So we pass in some Java object, we pass in the offset in that object we want to be updated, and we give the value to update it with. So this is going to atomically update that value by taking its current value and adding the delta value to it. So we're basically going to atomically update and add to that value at that object at that offset. All right, so far so good. Here's what happens. This particular piece of code uses the compare and swap long method, which is the one we get from the Unsafe class. And this is a lock-free call that runs atomically. So this call here is guaranteed by hook or by crook to always run atomically. Meaning that nothing else, remember atomic means indivisible. Nothing, it either happens all or nothing. So what happens here is offset is relative to the start of object O. So let's say for sake of argument, offset is 4, which is probably what we would get if we were dealing with a value in an atomic long object. So what we say is use compare and swap long to start at this location in memory and offset it by, say, 4 bytes. And the value v, which is the second parameters, the third parameters that's passed to compare and swap long, is the current value at that offset in memory. So here we go and we get this, we go here, we get the value at this offset and we slam it into v. So now we've got the current value. Now here's the interesting thing. This is an atomic read. However, it might have been the case, and this is really, really, really subtle. It might have been the case that between the point where we read the value at this offset and stored it into v, that another thread came along and changed that value. So that's why we have to run this thing in a do-while loop. And what we're going to do is in that do-while loop, we're going to check to see, is the value at this offset in this object still v? And if it is, we're going to atomically add delta to it, which will then update the value of v. But if v has changed because somebody snuck in between this piece of logic and this piece of logic, then we're going to loop back around again. And we're going to keep doing this until we actually have a consistent value of v, and then we're going to atomically update it to this by adding delta to it. Really, really subtle code. This is why we are very thankful that somebody took the time to write this code for us, and I'm teaching it to you so you'll be a better understanding of concurrency and so on, but you luckily don't have to know a lot about this. Okay, so now that we've got get and add long, so just this layer upon layer, right? You notice we had compare and swap long, which is like a hardware level thing. We have get and add long, which is still a very low level unsafe kind of thing from the unsafe class. And now we can finally implement our atomic long operations like get and increment and get and decrement. Get and increment and get and decrement are kind of like, I++ or I minus in Java or C++. You're getting the current value and then you're incrementing it. So we would call this a post-increment, post-decrement kind of operation. So what we're doing here is we're implementing get and increment and get and decrement by using get and add long, going off of this object, which is the object of atomic long for which get and increment or get and decrement is being called. We're taking the value offset, which is the value offset that we got from that reflection stuff. I probably should have used that up there. And then we're going to go ahead and add 1 to it or subtract 1 from it. So this is where all the magic is happening to do the increment and decrement atomically. So you can see the layering that's taking place. It's really cool. There's also another method defined on atomic long, and this answers the question we just talked about. How do you see compare and swap exposed to you as application developers? This is actually pretty important. It's actually, for some reason, not called compare and swap at this level. It's called compare and set. Who knows why? And you can see what happens is compare and set on an atomic long will atomically update the value to the if the expected value equals the current value. And the way it does that is it uses compare and swap long. So you can see it uses this value offset expect update. So this of course is the object that we're calling compare and set on. Value offset is that field that I don't show here, but it's the one that keeps track of the offset. And then we pass in the 2 parameters. So again, you can see these layerings that are taking place here to get a super duper efficient code under the hood. There's some other methods here that are also pretty interesting. Here's one that I like. This is called get and update, and it atomically updates the current value with the results of applying the given function, returning the previous value. And so you can see how this works. We have a do-while loop, again, for the same reasons we had before, because we have to make sure that nothing changes unexpectedly. We get the current value. We go and we compute a new value as a function of the previous value. So we get the current value, we're going to update it using this update function long unary operator. So we get the next value. And then we check to see, did the current value, the original value, change between the point where we read it and we computed the next value? If the answer is no, then we atomically update the previous value to the next value. If it changed, however, then we loop back around again. So we keep spinning until we can atomically apply the value of the function to update the value of the atomic long. And if you don't have a lot of contention, if there are not a lot of threads simultaneously pounding away on this particular instance of an atomic long, then this code will be super duper efficient. Because if you get lucky, you read the old value atomically, you update it, you're done. However, if there's tons of contention, let's say you're on a 64-core multiprocessor, and for some God knows why reason, all the threads and all the cores are banging away on this one poor atomic long, then you're going to have a lot of threads spinning because they're not able to atomically update stuff. Because when they go to read the value and then they go to try to set the value or update the value, it has already changed because someone else snuck in and updated it. So the lesson to learn from this is that atomic operations work really well when there's very little contention. But when there's lots of contention, then they may not work so well because you'll spend a lot of time spinning neurotically and not actually getting anything done. And as before, we return the previous value. And then, so this is get an update. Get an update gets the current value, updates the value, and returns the previous value. Update and get is similar to get an update, except it works the other way around. It updates the value and then returns it, as opposed to getting the current value, returning it, and then updating the value. And again, basically, the logic is almost identical. It just returns the updated value rather than the previous value. Okay, that's a lot to digest. That's implementing Java AtomicLong.